Hello everybody and welcome in this new video in which we will see a pair of exercises in which basically we extract the nth root of a complex number. These kind of exercises are really useful both for solving complex equations, but also because they allow us to think about the relationship between complex numbers in algebraic form and in polar form. As usual, before we actually start with the content of the video, I would like to thank you for the support you show towards my channel and my project in general, and I would like to invite you to renew this support. And you can then subscribe to my channel. You can hit the bell button to stay updated with all my new videos, and if you want to support me more closely, I will leave in the description below both my links to my personal and these projects PayPal and Ko-Fi. And with this incipit, I think we can actually start now. And so we want to extract the nth root of a complex number. So we start easy, and we start with this example. We have 8i under the cubic root, and we want to know which number is actually equal to the cubic root of 8i. So this is the equation we have to solve. So basically we rewrite it as z raised to the third power is equal to 8i. And when we encounter these kind of equations, namely some complex number raised to some power is equal to some other complex number, the most convenient way to solve this kind of problems is to switch to the polar representation of a complex number. So we have that we have to start with 8i because it's the number we already know. We know that 8i is evidently a complex number with modulus 8, and we know that the imaginary unit can be also written as e raised to I pi over 2, because we know that we can write this exponential as the 8. We have to continue to write it. We can write it as cosine of pi over 2 plus I, which multiplies sine of pi over 2. The cosine of pi over 2 is obviously 0, and we remain with the sine of pi over 2, which is equal to 1. So we have 8i, which is the number we started from. So this is its representation. Okay, now we have this unknown number z, and we know that every complex number apart from the origin can be written as rho, which with rho being the modulus, which multiplies e raised to I theta, being theta the angle between the x-axis and the radius which it identifies our complex number. So but now we have to remember that we are actually considering zeta raised to the third power, and these kind of operations are performed really easily on complex number in the exponential form, and this is basically the reason why we use this form in this kind of problems. So we have z raised to the third power is equal to rho to the third power e raised to I 3 theta. I think that in English is said theta. So now we have a way simpler equation, because now we have to identify this part of the equation with this other part, and so we can proceed. We have that rho raised to the third power e raised to I 3 theta is equal to 8, which multiplies e raised to pi over 2. Perfect. Now we have to equate the moduli, and we have that rho cubed is equal to 8, which means that rho is equal to the third root of 8, which is equal to 2. And then we have that 3 theta is equal to pi over 2 plus 2k pi, because we have to remember that the trigonometric functions are periodic with period 2 pi, and then we can conclude this exercise solving this equation. We have that theta is equal to pi over 6 plus 2k pi over 3, with k which is equal to 0, 1 and 2, because we remember that when we extract the nth root of a complex number, then we have to consider is 0th, first and second root. Basically the periodicity of this function is given by is inherited by the periodicity of the trigonometric functions, and we have to go from k which is equal to 0 to k which is equal to n minus 1, and then we collect exactly k distinct roots. Okay, perfect. This was the first exercise and we have solved it. We can see another similar exercise in which we have, for example, this we can say this was okay, exercise 1, and then we proceed with exercise 2. So in this other exercise we have 1 minus I, and we take the fourth root, and we want to discover which complex number is actually equal to the fourth root of 1 minus I. So the equivalent equation we have to solve is z raised to the fourth power is equal to 1 minus I. And now we have to proceed in exactly the same manner. The only difference between this exercise and the previous one is in the fact that we actually have another complex number in the as a known term, and we have a fourth power, but the concepts we have to employ are exactly the same. So 1 minus I can be also written as follows. So we have to remember how to take the modulus of this number, and we have 1 squared because it's the real part, plus the imaginary part of this number is minus 1, so we have to elevate minus 1 to the second power, and then we take the square root, and we obviously obtain 2 under the square root, and then we have 2 square root of 2. Okay, and then we have to take the arctangent of minus 1 over 1, which is the arctangent of minus 1, which is minus pi over 4. And we obtain that the exponential representation of 1 minus I is equal to square root of 2 e raised to I pi over 4 with a minus here. Okay, perfect. Then we can rewrite our equation in the following way. We have that z raised to the 4th power is equal to, we said, square root of 2 e raised to minus I pi over 4. Okay, perfect. Then we remember that we have to write here a rho to the 4th power multiplied by e to the raised to I for theta is equal to square root of 2 I e raised to minus I pi over 4, and I should be doing correctly. Okay, and obviously the link between this writing here and this here is that we can write z as rho which multiplies e raised to I theta. Then when we take the 4th power, we have to elevate this whole expression to the 4th power, and we have rho to the 4th power e to 4I theta, and this is exactly what we have here. Then again we have to equate the moduli, then rho to the 4th power with square root of 2, and we have to equate the arguments of the exponentials. We also have a minus here. Okay, perfect. Then we have rho to the 4th power must be equal to square root of 2. Then we have that rho is actually equal to 2 raised to 1 over 2, again raised to 1 over 4, which makes up to 2 raised to 1 over 8. Okay, and then we have that 4 theta is equal to minus pi over 4 plus 2k pi, and yeah, we can finish here with theta is equal to minus pi over 16 plus 2k pi over 4, and okay, then we have minus pi over 16 plus k pi over 2 with k which goes from 0 to we extracted the 4th root, then k arrives to 3, and then with in this way, so with our 4 roots can be written as z subscript k is equal to 2 raised to the 1 over 8, which multiplies e raised to I theta k, with theta k which is determined by this expression. And this exercise is basically teach us how to extract the nth root of a complex number. Let me know if you want to see more exercises in this vein. And with this consideration, I would like to close here this video, and as always I thank you for your attention, and see you on the next video.